This video is a sample problem involving a collision. In a football situation, a halfback carrying the ball towards the line of scrimmage and a linebacker, a defensive player, seeking to stop the progress of the ball. We're given data, 120 kilograms for the linebacker, 80 kilograms for the halfback, and they're facing each other. They're going to go directly at each other. This will not be a glancing collision. The halfback is approaching the line of scrimmage at 5 meters per second. The linebacker is at 4 meters per second, relative to the ground, directly towards the halfback just before they collide. So a concept question first. Could we expect the horizontal momentum of the system to be constant, to be conserved, if both players jump into the air at the instant before the contact is made, and they're not in contact with the ground? We'll get to that in the next slide. Calculate the velocity of the two players after the tackle is made. And is the kinetic energy of the system conserved? Is it constant before and after the collision? So those are some of our questions that we'll deal with. So first, on the horizontal momentum of the situation. Both players jump into the air. This is not good football technique. You should keep your feet on the ground when you're being tackled and when you're tackling somebody else. But this is a physics problem, so we're going to make both players jump into the air. When they both are in the air, and we ignore air resistance as a small effect, in the horizontal direction, there's no external force on the players. So there is gravity pulling the players down, but this is a problem worked out in the horizontal direction. So in this case, there is no external force acting on our two players. If there's no external force, momentum is conserved. Momentum is constant. So the answer is true. The horizontal momentum is conserved. So now we have a tool to calculate the velocity. We can use the principle of conservation of momentum. Momentum is mass times velocity, and we'll calculate this before the collision and write an expression for after the collision. We're going to let the halfback be in the positive direction. So we have two objects to consider before the collision takes place. There's the halfback and there's the linebacker. The halfback, 80 kilograms plus 5 for velocity. The linebacker, 120 kilograms. The linebacker is moving in the negative direction. So I put a minus sign on the number for the linebacker's velocity. We do mass times velocity for both objects, and we have a net of minus 80 kilograms meters per second. That's our momentum before of the total system of the two objects. After the collision, they're in contact. There's a tackle being made. The linebacker is grabbing on to the halfback. So now there's only one object. The mass will be 200 kilograms, the 80 plus the 120 for the two individuals. And then unknown is the velocity after the collision. That's what we want to calculate. So let's carry this on to the next slide and do the calculation. Conservation momentum. We've worked out the calculation of how much momentum there is before the collision, minus 80 kilograms meters per second. Our expression for momentum after the collision has an unknown in it, the velocity after. That's what we're seeking to find. So we could equate these two. mv before is equal to mv after. So minus 80 kilograms meters per second is equal to 80 plus 120 in parentheses times velocity after. You might want to pause here, pull out your calculator and do this. We're taking minus 80 divided by 200. I came up with minus 0.4 meters per second. This means we're going back away from the line of scrimmage. The ball does not cross the line of scrimmage. The halfback does not cross the line of scrimmage. And the linebacker has succeeded in stopping the motion of the ball. And of course they're going to follow the ground, and then our velocity will be 0. But in the air, at the moment of the collision, the velocity of the two individuals together minus 0.4, and they have the same velocity. It was a tackle situation, so there's only one object. What about the kinetic energy? Momentum was conserved. Is kinetic energy conserved? We calculate kinetic energy with 1/2 times the mass times the square of the velocity. Well, we can do this. We have all the numbers to do this before and after the collision. Before, we have two objects, so we have 5 meters per second squared for the velocity of our halfback, and we have minus 4 meters per second squared. Notice this is going to be squared, minus 4 meters per second. This velocity also will be squared. Kinetic energy is a positive here. We're squaring both velocities. One velocity happened to be negative, but the square will make that into a positive quantity. Again, you might want to pause the video and pull out your calculator, but I came up kinetic energy for the halfback is actually bigger than the magnitude of the kinetic energy for the linebacker. So 1,000 and 960, we get 1,960 joules. After the collision, we have one object, 200 kilograms, and its velocity is minus 0.4 meters per second. That has to be squared. That'll give us a positive here. And then times 100, we'll come up with 16 joules. And notice we have in the thousands of joules before the collision, we have 16 joules after the collision. Kinetic energy is not constant. And this is a characteristic of inelastic collisions where objects do not bounce off of each other, but where they, in this case, it's a perfectly inelastic collision where the two objects stick together. And just for fun, calculate the percent of kinetic energy lost, and it's huge. As the system almost came to rest, which would be 100% loss of kinetic energy, but there we are. Kinetic energy is not conserved in inelastic collisions. If you'd like to view more of these sample problems worked out step by step, I have a list of them at my simple website, gpclements.com. This website has YouTube videos grouped by topic, grouped by the concepts for both physics and astronomy, and some miscellaneous content as well. But this content is all free. You're not allowed to resell it, but it's all free. You don't give me your name, you don't register, you don't give me an email address, and my website does not put cookies onto your computer. So I hope you keep working sample problems in physics and ask your instructor when you have questions.